Section 5.3, Sublevels and Orbitals. We have seen that the protons and neutrons are contained within the small, dense nucleus of an atom. However, it's the electrons within the atoms that determine the physical and chemical properties of the elements. Therefore, we will look at the arrangement of the electrons within the large volume of space surrounding the nucleus. There's a limit to the number of electrons allowed in each energy level. Only a few electrons can occupy the lower energy levels, while more electrons can accommodate it in the higher energy levels. The maximum number of electrons allowed in any energy level is calculated using the formula 2n squared. 2 times the square of the principal quantum number shows the maximum number of electrons allowed in the first 4 energy levels. Energy level 1 can only hold 2 electrons. Energy level 2 can hold 8. Energy level 3 can hold 18. Energy level 4 can hold 32. Sublevels. Each of the energy levels consists of one or more sublevels, of which electrons with identical energy are found. The sublevels are identified by the letters S, P, D, and F. The number of the sublevels within an energy level is equal to the principal quantum number n. For example, the first energy level, n equals 1, has only one sublevel, 1s. The second energy level, n equals 2, has 2 sublevels, 2s and 2p. The third energy level, n equals 3, has 3 sublevels, 3s, 3p, 3d. The fourth energy level, n equals 4, has 4 levels, 4s, 4p, 4d, 4f. Energy levels of n equals 5, n equals 6, n equals 7 also have many sublevels as the value of n, but only s, p, and d and f sublevels are needed to hold the electrons of the atoms of the 118 known elements. Within each energy level, the S sublevel has the lowest energy. If there's any additional sublevels, the P sublevel is the next lowest energy, then the D sublevel, and finally the S sublevel. The order of increasing energy of sublevels of energy level is S is the lowest, is less than P, is less than D, is less than F. Orbitals. There is no way to know the exact location of an electron in an atom. Instead, scientists describe the location of an electron in terms of probability. The orbital is the three-dimensional volume in which the electrons have the highest probability of being found. As an analogy, imagine you can draw a circle within a 100-mile radius of your chemistry classroom. There's a high probability of finding you within that circle when your chemistry class is in session. But once in a while, you may be outside that circle because you were sick or your car didn't start. Shapes of orbitals. Each type of orbital has a unique three-dimensional shape. Electrons in an s orbital are most likely to be found in a region within a spherical shape. Imagine you take a picture of the location of an electron in an s orbital every second for an hour. When all these pictures are overlaid, the resultant, called probability density, would look like an electron cloud showed in figure 5.6a. For convenience, we draw this electron cloud as a sphere called an s orbital. There is one s orbital for every energy level starting with n equals 1. For example, the first and second and third energy levels, there are s orbitals designated as 1s, 2s, and 3s. As the principal quantum number increases, there is an increase in the size of the s orbitals, although the shape is the same. See figure 5.6. The orbitals occupied by p, d, and f electrons have three-dimensional shapes different from those of the s electrons. There are 3 p orbitals starting with n equals 2. Each p orbital has 2 lobes like balloons tied in the middle. The 3 p orbitals are arranged in 3 perpendicular directions along the x, y, and z axes around the nucleus. As with the s orbitals, the shape of p orbitals is the same, but the volume increases at higher energy levels. In summary, the n equals 2 energy level, which has 2s and 2p sublevels, consists of 1 s orbital and 3 p orbitals. Energy level n equals 3 consists of 3 sublevels, s, p, and d. The d sublevels contain 5 d orbitals, which gets a little crazy. Energy level n equals 4 consists of 4 sublevels, s, p, d, and f. In the f sublevel, there are 7 f orbitals. The shapes of the f orbitals are complex, and so we've not included them in the text. Orbital capacity and electron spin. The Pauli exclusion principle states that each orbital can hold a maximum of 2 electrons. According to a useful model for electron behavior, an electron is seen as a spinning on its axis, which generates a magnetic field. When 2 electrons are in the same orbital, they will repel each other unless their magnetic fields cancel. This happens only when the 2 electrons spin in opposite directions. We can represent the spins in the direction of the same orbital with an arrow pointing up and another arrow pointing down. Number of electrons in sublevels. There is a maximum of number of electrons that can occupy each sublevel. An s sublevel holds 1 or 2 electrons. Because each p orbital can hold up to 2 electrons, the 3 p orbitals in a p sublevel can accommodate 6 electrons. A d sublevel with 5 d orbital can hold a maximum of 10 electrons. With 7 f orbitals, the f sublevel can hold 14 electrons. As mentioned earlier, higher energy levels such as n equals 5, 6, and 7 would have 5, 6, and 7 sublevels, but those beyond sublevel f are not utilized by the atoms of the elements known today. The total number of electrons in all the sublevels add up to give the electrons allowed in the energy level. The number of sublevels, the number of orbitals, and the maximum number of electrons for energy levels 1 through 4 are shown in figure 5.2. 5.2, energy level 1. There's one sublevel, it's 1s, with 1 orbital in it, with 2 electrons total. 2 has 2 sublevels, s and p. There is 1 orbital in s, 3 in p, for a total of 8 electrons. Energy level 3 has 3 sublevels, s, p, and d. There is 1 orbital in s, 3 in p, 5 in d, for a total of 18 electrons. Energy level 4 has 4 types of sublevels, s, p, d, and f. S has 1 orbital, p has 3, d has 5, f has 7, for a total of 32 electrons.